Increased power, crisp throttle response, and more efficient combustion of fuel are just a few of the benefits that modern carburetor design offers. In order to deliver these benefits, all the circuits within a carburetor must be operating correctly. Understanding how each circuit works and how they interrelate is essential for the proper servicing and repair of carburetor systems. This video will provide a better understanding of how carburetors work, their construction and fuel delivery circuits, the different types of carburetors, and their unique features. All carburetors operate on the same basic principles and perform the same three basic functions. First, they supply atomized fuel to the intake tract. Atomization is the breaking down of a liquid into very fine particles, like a spray or mist. Fuel in this form can be readily mixed with the incoming air. Second, the carburetor must mix the correct amount of air with the atomized fuel to match the engine's requirements. This mixture is known as the air-fuel ratio. The air-fuel ratio is the proportion of air to fuel measured by weight. Third, the carburetor must provide a means for controlling engine speed. This is done by varying the amount of air that is allowed to enter into the engine by using either a slide or butterfly throttle valve mounted inside the carburetor body. As the slide is raised or the butterfly valve opened, a greater quantity of air-fuel mixture can flow into the engine. As air moves through the carburetor, it is necessary to introduce fuel to produce the correct air-fuel mixture. This is done with the help of a venturi. A venturi is a short tube with a tapering constriction in the middle. As air is drawn through the venturi, its speed increases because of the smaller area of the passage. As the air speed increases, there is a corresponding reduction in air pressure within the venturi. This low pressure area is created just above a tube coming from the float bowl. In turn, the float bowl is vented to higher atmospheric pressure. The resulting difference in air pressures causes the fuel from the float bowl to be pushed through the tube and into the venturi. At any given engine speed, the smaller the venturi, the higher the air speed, and thus the lower the pressure. Most carburetors take maximum advantage of this relationship by having a movable slide in the venturi area to vary the venturi size. These carburetors are called variable venturi carburetors. To better understand these concepts, let's look at the components of one type of variable venturi carburetor called a slide carburetor. First is the carburetor body. The carburetor body is precisely cast, then machined, and supplies the location points for the rest of the carburetor components. The carburetor throat is machined into the body and contains the venturi. A slide mounted inside the carburetor body offers a means to control airflow and vary the size of the venturi. Located at right angles to the center of the venturi, the purpose of the slide is to vary the amount of air that is available to the engine. Located inside the slide, a return spring ensures that the throttle returns to the closed position when released. The float bowl contains fuel, is vented to atmospheric pressure, and may include an overflow tube. One or more hollow floats made of plastic float on top of the fuel and help to control fuel flow into the float bowl. The floats are attached by an arm to the carburetor body and held in place by a locating pin. The floats pivot on the pin as the fuel level rises and falls. A float needle and needle seat are located inside the float chamber and act as a control valve that maintains a consistent amount of fuel in the float bowl. As the floats drop, the needle drops away from the seat, allowing fuel to enter the float bowl. As the float bowl fills with fuel, the floats raise, pushing the float arm against the needle and into the seat, preventing more fuel from entering the float bowl. The carburetor assembly includes several gaskets and O-rings that prevent fuel from leaking out and air from leaking in. To provide the proper air-fuel mixture at all throttle openings, several fuel metering circuits are used. The pilot circuit provides the proper amount of fuel from 0 to 1/8 throttle openings. The circuit consists of an air bleed, On some models, a pilot air jet, pilot mixture screw, one or more pilot discharge ports, and one or more bypass ports. The pilot jet is the smallest jet in the carburetor and is either pressed or screwed into a passageway in the lower part of the carburetor body. One end of the jet is submerged in the fuel in the float bowl, with the other end leading to an outlet port in or near the venturi. The size of the jet opening determines the maximum flow rate of the jet. Located in the air intake side of the carburetor body, the air bleed aids in the atomization process by mixing air with the fuel. Air enters through the air bleed and travels down a passageway to the pilot jet. The air then passes through holes in the side of the pilot jet and mixes with the fuel. Some carburetors use a pilot air jet to meter the amount of air entering the air bleed. The amount of air that reaches the pilot jet is determined by the size of the air bleed or pilot air jet. Positioned on the engine side of the carburetor, the typical pilot mixture screw varies the air-fuel mixture entering the engine during low engine speeds. By turning the mixture screw out, the screw's tapered end allows more of the air-fuel mixture to enter the carburetor. This increases the pilot circuit's discharge. Turning the mixture screw in allows less air and fuel into the carburetor, decreasing the discharge. It should be noted that some carburetors have a pilot mixture screw on the air intake side of the carburetor. In this position, the screw controls the amount of air entering the pilot circuit, thereby affecting the circuit's discharge. This reverses the adjustment procedure when adjusting the pilot mixture screw. Once the air and fuel have begun the atomization process, the resulting mist travels through a passageway to the pilot discharge port or ports. Located on the engine side of the slide, the discharge port allows the air-fuel mixture to enter the carburetor where it can then be used by the engine. One or more bypass ports, located under the slide on the engine side of the venturi, aid in the transition from just off idle to mid-range. With the slide closed, the bypass port acts as an air intake for the pilot circuit, aiding in the atomization of the fuel. As the throttle begins to open, the port switches from providing air to adding fuel into the carburetor throat, which provides a richer air-fuel mixture to the engine. The slide cutaway determines the air-fuel mixture from 1/8 to 1/4 throttle openings. The circuit uses a cutaway section of the slide to determine the amount of air that is mixed with the incoming fuel. Fuel for the circuit is provided by the pilot and mid-range circuits. An angle cut into the slide on the air cleaner side increases air velocity at low throttle openings. The increased air velocity decreases the air pressure in the venturi, allowing more fuel to enter the carburetor. The height of the cutaway portion determines the amount of air entering the venturi. The larger the cutaway, the leaner the air-fuel mixture. The mid-range circuit provides the proper air-fuel mixture at 1/4 to 3/4 throttle openings. There are two types of needle circuits, bleeder and primary types. Both types use a needle jet, jet needle, and air jet. Pressed or screwed into a passageway in the lower portion of the carburetor body, directly under the center of the slide, the needle jet operates in conjunction with the jet needle to control the amount of fuel available at mid-range throttle openings. In a bleeder-type circuit, the body of the needle jet has holes in it. This allows the air from the air bleed to be pre-mixed with the fuel for better atomization. In a primary-type circuit, the needle jet has no hole. The air and fuel are not mixed until they reach the venturi. The amount of fuel flowing through the circuit is determined by the clearance between the needle jet and the jet needle. As the needle is lifted out of the jet, the clearance increases, allowing more fuel to flow into the carburetor. Fuel for both types of circuits must pass through the main jet before it can be metered by the needle jet and jet needle. However, since the main jet will allow more fuel to pass than the needle circuit uses, the main jet does not affect needle circuit operation. During 3/4 to full throttle, the main circuit determines the proper amount of air-fuel mixture to deliver to the engine. The main circuit consists of a main fuel jet and a main air jet. The main jet is usually located near the bottom of the needle jet. The diameter of the orifice in the main jet is the final factor in determining the amount of fuel that is available to the circuit. Fuel for the main circuit is metered by the main jet and passes through the needle jet into the venturi. Clearance between the jet needle and needle jet is so large at this throttle opening that they no longer meter the amount of fuel entering the venturi. The main jet alone now controls fuel metering. The main circuit uses the same air jet used in the mid-range circuit to provide air to pre-mix with the fuel before entering the venturi. Although individual circuits are dominant during particular throttle openings, all circuits must work together, as there is some overlapping from one circuit to the next. The carburetor body incorporates some type of cold starting device to help provide a richer fuel mixture when the engine is started during cold conditions. The most common types of cold start circuits used are the choke plate and enrichment circuit. In the choke plate circuit, a butterfly valve located on the air cleaner side of the venturi is used to restrict the amount of air entering the carburetor. When closed, the butterfly valve reduces the pressure in the venturi, allowing fuel from both the pilot and mid-range circuits to enter the carburetor. At the same time, less air is allowed to enter, providing a rich air-fuel mixture. An enrichment circuit is an air-fuel metering circuit separate from other carburetor circuits. Fuel for this circuit is drawn from the float bowl through an enrichment or starter jet. Air for the enrichment circuit flows into a passage at the air filter side of the carburetor. This passage bypasses the carburetor throat and venturi. The enrichment circuit is usually controlled manually by a cable or linkage, which operates a plunger. When the plunger is down, the enrichment circuit is blocked. When the plunger is raised, a rich air-fuel mixture is discharged from the enrichment port. This port is located between the engine and the throttle slide. An enrichment circuit works best with the carburetor slide closed. High vacuum behind the closed side can then easily draw air and fuel through the enrichment circuit. Some carburetors are equipped with an accelerator pump circuit. The accelerator pump circuit discharges a metered amount of fuel into the carburetor throat as the throttle is opened. This helps to prevent any hesitation during sudden opening of the throttle. This is necessary because when the throttle is opened suddenly, vacuum drops in the venturi, causing a momentary reduction of fuel flow through the needle and main jets. This lean condition could cause the engine to hesitate or stumble. For further information on accelerator pump circuits, consult the video reference manual. Kawasaki vehicles commonly use one of three carburetor types: slide, constant velocity, or a fixed venturi carburetor. The main difference in the design of these carburetors is the way that the venturi is changed. Since we've already examined a slide type, let's look at the differences on the other types of carburetors. The fuel metering circuits in a constant velocity or CV carburetor are similar to those of the slide type carburetor. The major difference is a CV type carburetor uses a butterfly throttle plate to control airflow into the carburetor and a vacuum-operated slide to control the venturi size. As the throttle plate opens, airflow through the venturi increases and the pressure drops. A hole in the bottom of the slide connects the venturi to the area above the diaphragm. A separate port allows outside atmospheric pressure to reach the area below the diaphragm. The resulting difference in air pressures forces the diaphragm and the slide upward. When the throttle plate is closed, airflow decreases and pressure differences between the top and bottom of the vacuum slide assembly begin to equalize, causing the slide to move downward. While not directly connected, the throttle plate and vacuum slide work in conjunction to control engine speed. The fixed venturi carburetor is a relatively simple, compact carburetor. It uses a butterfly valve as the only means of controlling airflow through the venturi. A fixed venturi carburetor uses three basic circuits to meter fuel: a float circuit, a pilot or slow circuit, and a main circuit. The float circuit keeps the fuel in the float bowl at a constant level. The fuel level in the float bowl affects how rich or lean the engine will run through its entire range. If the fuel level is too low, the pressure difference between the venturi and the float bowl will be too low to force enough fuel up the feed tubes. The resulting effect will be a lean air-fuel mixture. On the other hand, if the fuel level is too high, the fuel will be too close to the outlet ports, causing excess fuel to enter the venturi. The result will be a rich air-fuel mixture. The pilot circuit meters fuel from idle to intermediate throttle opening. Air for the pilot circuit enters through the air bleed passageway on the inlet side of the venturi. On some models, air is also metered by the pilot screw. The fuel is drawn through the main jet to the pilot jet. The pilot jet meters and mixes the fuel with air in the air bleed tube. The resulting air-fuel mixture passes through a drilled passage in the carburetor body. The air-fuel mixture then enters the bypass chamber and travels to the pilot discharge port. A tapered needle, the pilot mixture screw, controls the air-fuel mixture flow through the pilot discharge port. As the pilot screw is turned in or out, less or more air-fuel mixture is allowed to pass into the airstream in the carburetor throat. This provides for adjustment of the air-fuel ratio at idle. As the throttle is opened, the bypass discharge ports are exposed to venturi vacuum, and more of the air-fuel mixture is discharged into the airstream. Pilot jet size determines the air-fuel ratio in the bypass stage. The purpose of the main circuit is to meter fuel from intermediate to wide-open throttle positions. In the main circuit, fuel flows from the float bowl through the main jet into a bleeder tube. The bleeder tube mixes the fuel with air from the main jet air passage. This produces an air-fuel mixture. As the throttle plate is opened, engine speed increases because of bypass circuit operation. At the same time, vacuum increases in the venturi. When vacuum increases to a certain point, the air-fuel mixture begins to discharge through the main fuel nozzle. The air-fuel ratio for the main circuit is controlled by the main jet size. In this video, we have covered the theory, construction, and operation of the different types of carburetors used on Kawasaki vehicles. For a more detailed look at carburetors and their operation, consult the video reference manual included with this training program, or attend one of Kawasaki's hands-on training classes. Employees of authorized Kawasaki dealers can earn a completion certificate for this program by taking the corresponding quiz on the K-Tech Learning Center section of the K-Dealer website.